So yes, welcome everybody to this workshop. So here you can see the different aspects we're going to be today. First, we will have some introduction to the project, and then we will go through the cloud platform that has been developed, and also we will see more detailed some of the tools that has been also developed during the project. And finally, we will go through the decision support tool. And after all this presentation, we can have some question and answer section in case you need you want to ask something, or you can raise any comments. And finally, just to remember that it has already been said that this webinar is being recorded, so this will be already also available afterwards in the web platform. Thank you so much for joining, and I'll give the floor to my colleague Carlos.
Okay.
Thank you.
Okay, welcome. Okay, so first, well, I would like to thank all attendees today as coordinator of the project, and also thank the people from ITENE and from NovaMechanics for the hard work that they have been doing in the development of the tool that we are going to present today, which is one of the main outcomes of the project, and also for organizing this workshop. So, well, that's my turn. We will start with the first presentation, which, as Marca said, it's related with the general review of the project. As I mentioned, this DST, the decision support tool, is one of the main outcomes of the Diagonal project. Mainly for the people who is not directly involved or is not familiar with the project, this presentation will be very useful just to provide them with context where this tool was developed, and also to know. I'm going to present briefly the objectives of the project and some of the results. As I said, just to give context about this tool. So just to start, some points regarding the data of the project, or the general data of the project. Diagonal is a research and innovation action. Maybe we should say was, because today is the last day of the project. It is finishing today. So Diagonal was a research and innovation action that was funded under the 2016-2020 call, by design, from science to regulation with nanomaterials. The project started in 2021. The duration was 42 months, and as I mentioned today, it is finishing today, the last day of the project. Here in the slide, just highlight two links that you can find here. The first link is to the Diagonal webpage per se, where you can find different news and results of the project. And the second link is related to the Cordis webpage related to Diagonal, where you can also find the data of the project and also those publicly available deliverables. So regarding the different partners that are involved in the project, I said that 20 partners from 12 European countries and one of the USA are involved in Diagonal, including 10 SMEs, 2 large enterprises, and 10 universities and research organizations. So we have the two branches, let's say, the industry and also the research. And as I mentioned before, we have members from different institutions, not only from Europe, but also from the United States and from Asia. So why Diagonal? What is the main aim of this project? Well, as you know, nanotechnology is a key enabling technology. And in the last years, there was an increase in the number of nanoparticles due to their outstanding properties and their functionality that were being using in different sectors, such as the textile sector, health, automotive, electronics, and very long, etc. Since it is expected that the use of the nanoparticles will increase in the next years, so it's very important to know the impact that these materials could represent for the human health and also for the environment. And it's also very important in the case of those nanoparticles that present that are more complex, such as the multi-component nanomaterials, or they present heterogeneous morphologies, such as the high-aspect ratio nanoparticles. because currently the information that we have about their impact to the environment and to the human health is very scarce, because most of the works, most of the research is done, was focused on the pristine samples, and on simple nanomaterials, and also in pristine samples. In Diagonal, we're also considering the degradation products and the transformation products of this kind of nanoparticles, since they can also represent an impact for the human health and the environment, and this impact could be different than the pristine material. So this is something that should be taken into account when we study the impact of these materials. Here in the next slide, we will see a diagram that is representing the project concept. In Diagonal, we were working with the materials provided by 7 demonstrators. I will specify later in other slides the demonstrators that were directly involved in the project. So we were working with these materials and obtaining a lot of data that were used to validate and to develop modeling tools that are able to predict in some way the potential impacts for the health and for the environment that these materials can represent. We also have been considering the sustainability perspective, so different life cycle sustainability assessments were performed were analyzed the development of these materials. And the combination of the risk assessment with the life cycle sustainability with these combined studies, during the project, we have provided different strategies to the demonstrators that were applied in situ to the demonstrators to produce safer and more sustainable products. With this, we could adapt the risk assessment guidelines and also the existing risk management strategies, as well as to support at these governance levels regarding the special needs that these special nanomaterials, multi-component nanomaterials, and HARNS represent. And finally, just mentioned that Diagonal has been working in collaboration with other initiatives and other projects. For example, just mentioned the other MVP 16 projects that we were in close collaboration in several topics. Something that makes sense because we were funded with the same goal. So basically, we have the same objectives to study the impact of these materials. Regarding the demonstrators involved in Diagonal, as you can see in this slide, we have representatives from different fields, including the automotive sectors, the coatings, textiles, industrial flooring, printed electronics, and also cosmetics and biomedical industries. So a very heterogeneous group of fields. And these demonstrators have been collaborating with us, providing samples, industry insights, and also, as I mentioned before, applying the SSbD strategies identified in the project and testing them in real scenarios in their own facilities, and testing if these strategies are useful or not, if they are able to produce safer and more sustainable products, and also keeping the functionality, something that is very important for them, because if we cannot keep the functionality of a product, it makes no sense to apply these strategies. In this slide, just very brief to mention some of the achievements obtained in Diagonal. At risk assessment level, we help to increase the knowledge on the nanomaterials and HARNS, helping to understand the implications for human and environmental safety and sustainability in several branches. We have physicochemically characterized all the materials along their life cycle, not only the pristine materials, also some transformation products. We have performed different toxicology assays using representative advanced models for human exposure and also for ecotoxicity. We also perform fate, behavior, and environmental exposure studies, for example, performing campaigns in the own facilities of the monitoring campaigns in the own facilities of the demonstrators to study the levels of nanoparticles in different environments, and also performing life cycle sustainability assessments. As I mentioned before, all these data that we have been obtaining during the whole project were used to develop and validate multi-scale modeling tools that will be able to predict the potential impacts of these materials. These tools will be explained more in detail in the following presentations. At risk management level, as I mentioned before, we have developed different SSbD strategies that, as I mentioned, were applied directly in the demonstrators to demonstrate their feasibility and if they are working well. And at risk governance level, we have reviewed the legal status of multi-component nanomaterials and HARNS, the current legal status. And also we have developed the diagonal DST that, as I mentioned, is the main outcome of this project, and it is the focus of this workshop. Some numbers to highlight in diagonal: 20 scientific publications were produced, 5 workshops were held, 2 training materials were produced, 3 webinars were held, and also 39 conferences were attended by members. Regarding the SSbD decision support tool, just give a very brief introduction of this tool. The diagonal SSbD DST is selected as a key exploitative result of the project, and it consists in an interactive DST, which is integrated into the Nalos Cloud platform that offers tailored SSbD strategies for HARNS and multi-component materials, reducing research and development time and cost while improving the sustainability of the safety. So it is a ready-to-use interface, able to guide decision-making and risk assessment of multi-component materials and HARNS. And also it is conceived as a flexible tool that it can accept contributions from different sources. We have developed it open, and it can be updated, integrating new models, new data that will make that can make this tool better, and also improving the accuracy of the results in terms of prediction of the impact of a new material that this DST can provide. And moreover, it can contribute to other alternative frameworks due to its modular structure. So the main objective of the DST is the suggestion of SSbD strategies, allowing the selection of the best available approaches to produce safer and more sustainable multi-component materials and HARNS. And as I mentioned before, a set of different tools and models are included in this tool. You can see here a list of them, but they will be explained more in detail in the following presentations. Regarding the target groups of the DST, we consider that all the branches involved in the development of new materials are interesting groups that could be interested in the use of this DST, including consultants, researchers, industries, and also regulators. This is a diagram of how this decision support tool works. As I mentioned, this will be explained more in detail, and a demonstration will be done in this workshop. But very brief, starting from some inputs that the user can provide to this DST. For example, some data for the nanoparticle they want to develop, including the amount that they want to produce, such chemical characteristics. Once this data is included in this decision support tool, the combination of the databases included in the DST and the tools regarding the risk assessment, risk management, and sustainability. After this analysis, as an output, the DST will provide suggestions of tailored SSbD strategies based on a scoring. And this will allow to produce safer and more sustainable nanoparticles. So the objective of this DST basically is to find alternatives to existing solutions, trying to find safer solutions, safer candidates to substitute some products that are currently using, but they present toxic issues. And also, one other of the objectives is to start new materials. So just trying to provide insights about their possible toxicity before starting their production. So regarding the benefits, as you can imagine, such a tool can provide a lot of benefits for the users, because if you can predict if a new nanomaterial or an alternative that you are developing is safer and more sustainable before starting the production, it will suppose a lot of benefits. For example, well, this diagonal SSbD tool is involves centralized access and availability of tools and models for better prediction of the material behavior and reduction of uncertainties. So you will have all these tools all together in the same place. And the production of safer and more sustainable products will involve cost savings in terms of cheaper testing, its regulatory compliance, etc. It will enhance the decision-making and low TRLs for novel technologies, the reduction of strategic and investment risks, and also the reduction time to reach the market once a material is starting to, let's say, to design. And in addition, it has another benefit, which is the increase of the consumer acceptance, since the sustainability is becoming a priority for consumers, and the sustainability is also included in the DST. So finally, as a summary, let's say that this tool is both usable and highly valuable for industry, providing a practical solution for the development of safe and sustainable nanomaterials. So that's all from my side for the introduction presentation. So thank you. I'm going to stop sharing.
Thank you, Carlos, for the presentation of the overview of the project. So maybe we can move on to the next presentation about the cloud platform. So Dimitra, will you share your screen?
So I guess you can see my screen?
Yes, we can see it now. Thank you.
Okay. And it's not interfering with the presentation, okay? Right, okay.
No, it's already in presentation mode.
Okay. Okay. Thank you very much. So,
thank you.
Good evening. I'm Dimitra Danai-Varsou. I'm a senior researcher in NovaMechanics. Today, I'm going to briefly present you the Diagonal Cloud Platform. NovaMechanics is an SME based in Cyprus and Greece, and our role in the Diagonal was mainly focused on data management and in the development of the Diagonal Cloud Platform and the integration of the different tools developed under the project, and the DSS and all the tools that we're going to discuss today. So, just a few words about the necessity of a cloud platform. In general, in the nanoinformatics field, we start from experimental data or other data like theoretical data, literature data, and we are trying to develop in silico models and in silico methodologies in order to predict the nanomaterials properties and the nanoparticles properties. And then we assess the quality of these predictions, and we guide the next, let's say, batch of experiments. And then the new data, we are just updating our models and etc. So this is the cycle of the workflow, let's say, in the nanoinformatics. And our goal in general is to help in materials prioritization for testing, to understand the properties that govern toxicity or to reveal mechanisms of actions, and understand the interactions of materials in different levels. So after the model development, an important step is the model dissemination, because the main, let's say, goal is that the model is finally used by the broader community or by regulators. So we are trying to deliver to the public ready-to-use web services and the user-friendly applications, where all the steps of data pre-processing, modeling, or data retrieval are performed in the background, and the user can use through an intuitive environment and can acquire reliable predictions for his or her data. So the Enalos Cloud platform is an online toxicity materials engineering and drug discovery platform, and hosts a series of predictive models released as web services that aim to address the needs of acquiring fast and accurate predictions of toxicity and other properties of novel compounds and novel materials, reducing at the same time the cost and the time spent in experimental procedures. This platform is freely accessible, and there is no need of any identification. And researchers and scientists worldwide can utilize its capabilities. It incorporates a diverse array of predictive models as web services, as I said before, leveraging both open source software like KNIME, Weka, R, Python, LAMS, Java, and proprietary software like Isalos and Enalos Plus Nodes. And the platform also employs the software as a service technology to ensure that these models are readily accessible and user-friendly for the scientific community. And this blend of software resources empowers the platform to offer robust and flexible cloud computing tools, simplifying complex scientific computations. The platform is designed with non-informatics experts in mind, and they aims to minimize the time and the resources needed for the experimental testing. It provides comprehensive training materials like manual, like YouTube videos, so that the users understand how they can use the different services. And also, you can see here, for example, that the intuitive graphic user interface offers, for example, radio buttons, drop-down menus, other buttons, some typing, offers also visualization capabilities, and all the files can be later downloaded for further processing offline. And some numbers about the Enalos Cloud platform. It hosts 50 user-friendly web applications under 7 broad tool categories. The web services are also supported by scientific publications, and we have also web services for more than 10 European projects. So the Diagonal Cloud platform is built upon the Enalos Cloud platform and works synergistically with ongoing and past projects and initiatives like NanoSolvit, NanoCommons, RISC-ON, etc., to maximize the data and tool harmonization and to ensure interoperability with existing platforms and facilitate, at the end, industry and regulatory acceptance and sustainability of the tools. State-of-the-art IT tools for distributed applications like the Docker and the APIs are used to integrate the project's database and in silico tools within the Diagonal Cloud platform. And the open architecture of the cloud platform ensures and supports its sustainability and evolution, as it can be continuously updated with the advances in the field and the tools from the different project partners or from the entire community. So, right now, the Diagonal Cloud platform hosts 7 web services. You can visit the cloud platform from this link or by just Googling it. And this is the interface where you can see the different tools here and the different projects and categories here. So the web services right now are the NanoTube Construct tool, the Zeta Predict tool, the NanoBioaccumulate tool, and the Risk Management Decision Support tool, the Electronic Laboratory Notebooks, and the database. So I will briefly present each one of the web services. The NanoTube Construct tool facilitates the digital construction of energy-minimized nanotubes composed of single-layer materials, allowing users to calculate atomistic descriptors critical for the understanding of the material properties. You can visit from this link the tool, and also you can also check the recently published work for the NanoTube Construct tool. in the SSbD journal. The ZetaPredict tool offers an innovative approach for calculating the zeta potential of nanoparticles by employing electron microscopy images of colloidal dispersions, along with theoretical modeling based on the DFDO theory and atomic force fields calculations. The NanoBioaccumulate tool is another tool recently published in SSbD, and it's designed for modeling the uptake and bioaccumulation of nanomaterials in invertebrate organisms, and provides valuable insights for conducting environmental risk assessment of nanomaterials. The Diagonal Risk Management tool supports regulatory bodies and industries and stakeholders in selecting the most appropriate risk mitigation strategies, and addresses exposure risks at various stages of the life cycle of high-aspect ratio nanomaterials and multi-component nanomaterials, ensuring compliance with safety regulations. The DST that you're going also to see today, that supports consultant researchers and regulators by facilitating the selection of the best available safety by design strategy for HARNS and multi-component nanomaterials. The electronic laboratory notebook system, which is designed for the collection and curation of experimental data related to nanomaterials. It supports the implementation of the Diagonal project's workflows and data management practices, ensuring data traceability and adherence to open science principles. And finally, the Diagonal database, which is a dynamic repository based on open and fair data principle, and accommodates various types of nanomaterial-related data, providing users with access to broad spectrum research outputs and datasets. So, I'm going now to focus to the nanotube construct tool. You will see how the different web services work. As I said before, with this tool we can construct nanotubes from single layer materials with non-zero thickness and various symmetries. We can visit the nanotube from this link, or we can just directly check the, I guess you can see my screen right now. From the Analyst Cloud platform, we can go to the Diagonal instance and select the nanotube construct tool. As you can see here, for each one of the services, we have a specified card with some information, a link to the publication, documentation, which, for example, is the manual of how we can use the different web services, and a link directly to the service. So here we can see, sorry, here we are, yes. Sorry. Right. Here we can see that the data are, the different materials are carbon-based and not carbon-based. We have different here novel materials like alpha graphene, beta graphene, graphidine, etc. We can select one of the materials from the radio buttons, and we wait till the unit cell is appears in the interface. So. At the end of this step, we can acquire, we can calculate different descriptors that can be input to different, let's say, machine learning models, and we can understand, can derive some conclusions on the stability of the nanoform in vacuum. So let's say here we have the unit cell of the material that we have selected. And the next step is to create the nanosheet and the nanotube. We select here the geometry of the nanosheet and the nanoparticle, and we press the button. So at this point, as you can see here, the unit cell that we have selected depending on the geometrical characteristics here, is replicated into the 2D space, and after that, it is rolled in this direction, like this, and forms the nanotube. So we are waiting here a little bit for this step. So here we have the nanosheet and the nanotube that resembles like a ring at this point, based on the geometry that we have defined here. And the last step is to perform the energy minimization. Depending on the material that we have selected on the first stage, we can select one of the available force fields. The application is designed so that the most appropriate force field is the first one of the list. We can tune here the energy minimization parameters, and we wait for the results. As you can see, we don't need any knowledge of deep programming skills or for informatics or for simulations, and just with some clicks, we can have here the results. What we can see here is the two sheets, the geometrically constructed and the energy minimized, one on the top of the another. So this is why it's like the sheet is shrinked. And here we have some results. We have the average potential energy of the nanosheet and the nanotube. And by comparing these two values, we can see here that the nanosheet in vacuum is more stable than the nanotube. And we have also different descriptor values that are also calculated. We can download these results for further, let's say, processing. And what we can get as a result are the different descriptors that we can use it, as I said before, in machine learning models. And we have here the different LAMS data files and XYZ files that can be also used for further simulation, for example, with membranes, etc. So this is the nanotube construct tool. And just a few minutes I will share for the zeta predict tool. It incorporates different technologies like the liquid TEM and the DLVO theory. And sorry. Yes. So we can visit the NLS Cloud platform again. I guess you can still see my screen. Okay, perfect. Okay, what we need to do is to upload an instance of the liquid TEM image. And then we have to provide the length, the measured length from the sorry, I have to do it again. So with this picture and some measurements on the picture, we can calculate the zeta potential of the depicted nanoparticles. First the scale bar and then the diameter of the core and the diameter of the cell. If the cell is not visible, it's the same as the cores, and the distance between the two centroids. And then we select what type of material we have depicted on the TEM image. Here we have gold, and the medium is water, so we select water from the list. We can also select another material, or we can browse and select a material from the periodic table. So here I select this force field for water, and we can calculate here the zeta potential of the particles. So this is the Zeta Predict tool. Again, it's an easy to use web application, and there's no need for any computational skills, and we get the reliable results for our materials. So that's all from my side. Thank you very much. If you have any questions, you can write me an email. Thank you.
Thank you so much, Dimitra. So maybe we can now move on to the other new model that has been developed. So Patricia.
Let's go. So I am Patricia from ICCRAM at the University of Burgos. First of all, I thanks for the opportunity to show the nanographene impact tool, this new tool. Why a nanographene impact tool? Well, the context is, as you know, the graphene nanoflakes have a structure property relationships that influence their interaction with biological system, potentially causing adverse effects. One structure property, for example, is the shape, rectangular versus hexagonal, no? Which can influence the interaction with biological system depending on its size. There are a growing need for robust methods to predict the biological interaction and potential toxicity of graphene nanoflakes. So that this tool, the nanographene impact tool, assigns a score to graphene nanoflakes under evaluation that reflects their biological interaction or impact on human proteins and membrane cell, from which the toxicity, we can say that can be inferred. Okay, next slide, please. Okay, how does the tool work? Well, the first step, we have obtained an exhaustive data set using in silico methods, very hard and extensive work behind this. This data set contains 43 descriptors related to different spatial, atomistic, electronic, and molecular descriptors, in this case for 33 graphene nanoflakes. This dataset contains also the data for the binding affinity of docking to 100 proteins, and also contain the data for different thermodynamic properties such as free energy, diffusion, entropy, and permeability predicted for 4 types of cell membranes. So the first step, obtain this dataset. Next slide, please. Okay. Next step is the development of random forest regression models. Okay, these regression models using random forest algorithm allow for predicting the biological interaction between graphene nanoflakes and proteins. In this case, through the relationship between average docking energy and nanoflake predictors, and with cell membranes through the relationship between average membrane data and nanoflake predictors. It means that for these random forest regression models, the training dataset used is the aforementioned dataset that I explained before. For the validation, we use also another external dataset, also obtained using in silico methods, as data not seen. Okay. Here you can see scattered plots showing the well performance of the model. You can see the relation between the predicted value through the models and the real values used. Okay, for the models related to interaction with membrane cell, and for the model related to interaction with protein. The R-square is for about 0.9. Okay, when we have these regression models with well performed, The next step is the calculation of the score. The score is a value between 0 and 1, combining both set of predictions, the predictions for the interaction between graphene nanoflakes and proteins, and the prediction for the interaction between cell membranes and nanoflake predictors. This score reflects the comparative impact of the graphene nanoflakes evaluated on proteins and plasma membranes together. Next slide, please. Okay, the tool needs input data. So the users upload their data, maybe using the SLSprite sheet contained inside the tool. And this SLSprite sheet is very simple, only contain the name of the graphene nanoflakes in one column and the necessary 43 descriptors data. Here we can see a prompt of the SL, and the acronyms, the descriptors are in acronyms, but into the tool there are the definition for each acronym to the corresponding descriptor. Next slide, please. Okay, when the data is uploaded, the models run, the predictions are obtained, and we can obtain the results. The user receive a table with the graphene nanoflake and their corresponding score. Also, the levels corresponding to the score. These levels are defined in low, medium, high, or very high, depending on the quartile where the score is. Okay, it means a low score indicates lower biological interaction or impact respect to the other graphene nanoflakes evaluated, from which minor toxicity may be inferred. Next slide, please. So the nanographene impact tool allows, in an easy way, evaluate the biological interaction or impact of different graphene nanoflakes on human proteins and membrane cell and infer potential toxicity. The tool is implemented or will be implemented into the cloud platform in the next few weeks, I hope. And also, although the performance of the model is strong, is expected to conduct more additional validation processes with additional external data set to enhance the confidence and generalizability. Also, I would like to say that we have in preparation a paper with this methodology and the results and the rationale behind this tool, and I think the paper will be submitted very soon. Okay, that's all. Thank you very much for your attention.
Thank you so much, Patricia. So then I will give my presentation about the decision support tool. First, I'm going to explain briefly how it works, and then we will move on to see some examples on the functionality. So first, a bit of background of this decision support tool. So this we have this safe and sustainable by design framework that aims to go beyond these legal requirements, providing different standards and suggesting different, in this case, what we do in the decision support tool is to suggest some strategies or alternatives. So, and this is this decision support tool is a main goal of this project and one of the main results. So just more background, like the project, as Carlos said, started in 2021, and then the current framework from the JRC was submitted after this date. So then we have to modify our the approach we were working on, and with the adapting this approach we had with the new SSbD framework, we came up with this stepwise approach to assess and suggest some strategies. So this decision support tool approach that we have finally implemented is this stepwise approach that evaluates 4 different steps: the hazard, the production, then the final application, and finally the sustainability of the material. And for these steps, the users have to go compiling information and providing information to the platform, and then the results are shown. So I will give you a brief approach on how it works. So we have an initial screen where some information about the material should be provided. Then we go to evaluate the step 1 about the hazard of the material. Here we also provide some information about the material. In this step is a control banding tool, what works behind. So we have selected different options for each input that should be provided. Each of the options has been given a score, and with this score we perform the needed equations to estimate the hazard score. Then we go to step 2, which is quite similar to step 1. It is also a control banding tool, but in this case, information not only from the material, but also about the task that is being evaluated is asked. And we go through the same steps to estimate some score for the production. And then we also, to have this score of exposure, we compare this information that we have computed in step 2, we compare with the information from step 1, because we need to take into account the hazard. Finally, well, then we have the third step about the environmental aspect. So here we have developed a fate model that also provides some score about how hazardous, about how this material could affect in the environment and also in the consumers. So we also compare the information that we obtain from the model with the hazard, because they are also related. And finally, we go to the 4th step about the environmental sustainability. In this step, by the moment, an LCA is needed, but we understand that it is not so easy. So we are maybe this is not the best way to approach, but this is what we finally came up with. So with the results of the LCA, we need to provide also a score. And when we have gone through all these 4 steps, we can see the results. So in this screen, the different strategies are suggested, and they are grouped by safe by material design, safe by process, and also safe by sustainability. And along with this information about strategies, we will have the results of all the assessment that has been done in the 4 steps. So maybe we can go and see how this works. So we go to the NLSCLAD platform in diagonal, and here, as it has been told, we can see the diagonal decision support tool. And then we can see here the initial definition of the material. So we give, for example, a name. I will set like an example. Then we have to select this nanomaterial family. For the example, we will select these silver nanoparticles. And then you could provide some information about the chemical composition. So here you could add or delete different components. So I will copy the ones I have for the example. And let's say that it's 60% in this case. Then the second component, let's say about 20%. And we have a third component with the gas. And let's say it's another 20%. In this case, for example, if we say here that we have a 15% in this example, so you can see that the percentage doesn't sum up to 100. So when we try to go to the next step, a message appears, letting you know that you are not evaluating all the material, just some components, and you can proceed with that if you want it, or you can cancel and then correct the component that you decide. So then we go to the first step. This is the hazard step, and here we evaluate the material. So we have the amount of material that is used. In this case, you can see from the different options, we will select the 100 to 50 to 500. Then we select the particle size, which in this case we will select higher than 100 nanometers. And then you have to introduce whether the material is functionalized or not. In this case, it is. And also introduce the shape. Then if you have here a list of hazard sentences that may apply to the material or not. So in this case, we will select a few of them. So you can see it's quite a long list. You can go through all of this list, and then once you have finished completing this, we go back to the app of the websites and we go to the next step. In this step is about the process. So we have information, and we have divided this in three main groups, which are the working area, then a description about the task, and more information about the material. So, for example, the working area, it is asked how the surface is. So in this case, we will select that is closed premises. Then we need to select the volume. Then whether there are ventilation or not. And then the maintenance of the of all the machines and equipment that is involved, and the cleanliness also. So with this information, we go then to the task description. First of all, it is here it is information about the exposure. So you can either provide a file with real measures, or you can select raw data and insert here the the concentrations of the average concentration for near field and far field. And if you don't know them, we have another tool that could calculate this. So with this information, we compile, we fill all the information here, and then we click compute. And with these two fields will automatically be filled. So for the example, I will upload some file. To upload the file, you have to first download the template. So for example, let's open the template to see how it's extracted. Okay, so here we have the template. Some random information is already provided just to know how you should fill this table. And with this information, once you have copy pasted the data from the different measures, you click the upload data file and you select the one. I have this one already prepared. So we upload it. You can see that there's the name of the file you have selected. And then we move on to the rest of the parameters that are asked. Here we select that very high manipulation energy. That task it's 2 to 4 hours a day. Then the number of exposed workers and the task frequency. All this information, like it's close to the worker. Then we have to also fill information about the protective equipment. So in this case, we have a nanoparticle hood, for example, and let's say that there's no respiratory protective equipment, but they use gloves and laboratory coats, so non-eye protection, but they wear safety shoes. They also, it is also needed to provide information whether some working procedure is established. In this case, yes. And finally, about the whether there are other sources in the area. And finally, more information about the material. So then we have the percentage of the nanometric percentage of the material, let's say 50 to 99, the shape that we have said it was spaced. Then you can also select that you don't know any of these parameters. And then, for example, 10 to 50% of the product is diluted, and we have low viscosity, for example. So we also go up to the top of the page, and we go to the next step. This is the fate model that has been developed. So I will include some parameters that are asked. This is a more precise model. It's not information that there are not options for these inputs, but you have to provide the precise data. So let's say, for example, that we have an initial emission of 500 kilos to the air, but there's no emissions to any other of the 4 components. So we will estimate, for example, a period of time of 10 months, let's say. Or you could select each of these. For example, you can change this to 1 year or 2 years. It depends on what you want to estimate. Also, the dimensionality of the material should be provided. In this case, we will have like 1D. And and also information about the particle diameter and more information about the material. I will compile it with the information I have compiled for the example. You can see here next to the parameter that which measures are used. So, and then the particle density and the length. So here the length of the 1D nanoparticle will be, because we have selected that it is a 1D nanoparticle. If we select 0D, here you can see that we don't have this option, and if it's 2D, it is asked another parameter. So let's say 1D, and then we need information about the area that is wanted to be evaluated. So, okay. This is quite a huge number because it is asking square meters. Then we will say 97% of soil in this system, and finally we will use 700 millimeters per year. So this step is takes quite a bit to run. So we will wait till it finished. So running this model is just that it takes quite a bit. Yeah, so now you have to provide the information about the life cycle assessment that has been performed. In this case, in the case that you don't have this information, you can just let all this filled with the default parameters. But as you can see, it's quite simple that just keep selecting the different options. So for this case, we will assume that no LCA has been performed. So it's something that we shouldn't take into account, but we then go to the results. And here we can see the different strategies proposed and all the output of these different models, all the scores from these steps. So, for example, we can see that we have a score of 3 from step 1, step 3, and then a bit lower, a score of 2 for the production process. And then you will have here the sustainability score, but in this case, that's as we assume that no LCA has been performed, then this shouldn't be taken into account. But if you have the LCA assessment, then you can relay this information, and if you need to improve the sustainability of the material, then it is suggested, for example, you go to the type of strategy, you see sustainability and the different options that you have to improve this step. So the same for the hazards and the production. If you have, in this case, we can see that we have the same score for hazard and the final application. So maybe we can try to reduce the hazard of the material, and this could be using material design strategies. So we will go to the material design strategies and look at the different options that are suggested. So that's something that the user need to choose. It doesn't provide some kind of better strategy that fit for the material, but is up to the user which one to use. So maybe if it is suggested that some of the material, maybe the size could be reduced, then you can go back to the step that asks for the size, update the size. For example, if we have a 450 nanometer material, and we think that maybe reducing the size, as it would be here on a strategy, saying reduce the size. So we know that, for example, we could reduce this material size from 550 to 300, for example, and then we go back and modify the parameters to see if it is expected a change in this, a reduction of these risk levels. So these risk levels, you can see that here's one, as we don't have information, but they will go, the 4 of them go from 1 to 5. And you could see the different colors in the background that suggest whether it's good or not quite good. So in this case, 1 represent it's have a green background because it's the best score that you could be obtaining. And then if you obtain a 5, for example, the background would be red. So I think that's all from my side. So this is how the decision support tool works. I will stop sharing, and there are a couple of minutes if you have some questions for any of the presenters, or you have some suggestions.
Yes. Blanca,
Yeah.
hi. I have a question, and congratulations for the tool. I think it's very promising. It's exciting to use it. I have a question because I see that the tool does not allow empty space. So all the values are critical to the assessment?
Do you mean in all the steps or in one specific?
I don't know. It's a general question. Yeah.
So by the moment, like all these parameters are needed to run the model. Okay. But we understand that sometimes it's not quite easy to get this information. Mm-hmm. So at this moment, we cannot propose like some database or something where to extract this data. Okay. Also, maybe it should be extracted maybe from literature, but we understand that some of the parameters are quite tricky to obtain.
Mm-hmm. Okay. Thank you.
I do have a question because I was curious about the IP of the tool. Did we try to patent something, or the models or something, or not?
No. So the models that run behind the tool are models adapted for this project, the diagonal project, and we have been working on this during the project, but there's no patent for this. So we didn't do anything from this. Yeah.
The project is already finished today. Is this still available online, and who will keep it? Probably you have already mentioned this, but I didn't hear.
Yes, so this decision support tool will be available online in the SSbD platform from NovaMechanics. So maybe Dimitra know how long it could be available?
I guess forever. I mean, we are not planning to remove it from this. It will stay like an instance of the tools for the broader community. So the goal is that the tools remain there and they're updated later, maybe in collaboration with other projects. So they will stay up there.
Thank you.
Okay, great. Thank you. Thank you so much, and congratulations again.
So maybe we can end this workshop here. So I just wanted to thank you all from joining, and thank you also all the presenters that has been have shared this presentation. So thank you all so much. Thank you for joining. And if you may have any questions afterwards, you have our emails that has been already in the presentations. And this webinar, as we said before, will be available in the web of the project. Sorry. So thank you all so much.